Hello? Hello?
Yeah, I can hear you.
I hear you? No. Hello everyone, and thanks for giving this opportunity to talk with my job. This slide is called porting MADGRAPH to an FPGA. First of all, what is MADGRAPH? You can see this MADGRAPH in simple terms is a Monte Carlo event generator for collider studies. So nowadays is widely used for event generator. This is a simplified block diagram. On the first of all, you need to generate the random numbers. Once you have the random numbers or random events, you pass to calculate the kinematics of the initial and the final state of the particles for each event. You obtain the momenta, and finally you calculate the matrix element of each event of particles. Here you can see the frame graph. Frame graph is a very powerful tool. The frame graph is very useful to detect the bottlenecks of your processes and your platform. In this frame graph, the total program on CPU is the 80% of the CPU resources. The 60% is the MADGRAPH calculation, and the Python code for the program. If you see the math event is the 60%, but the matrix element is the 40% of the GPU resources. So in the next frame graph is for a more complex process. For this number of events, I execute the 9 hours. So in this case, the math event is the 90% of the CPU resources, and the matrix element is the 61% of the resources of the CPU. So if my bottleneck is the matrix element calculation, the MADGRAPH GPU group think, okay, I will port this part and obtain some results. The algorithm is the same. You generate the random numbers, calculate the kinematics, obtain the momenta, and obtain the matrix element calculation. Okay. If you see this part is the matrix element calculation, the part of the GPU port, and it parallels the matrix element calculus. So comparing the results for a simple process, I obtain an speed around the four times, but for a complex process, the speed up it's around the 120 times for a reduced number of events. But this is an extrapolation. If you use more number of events in CPU, it takes around 3 months, and the GPU it takes around 13 hours. I don't prove the CPU test, but you know. So seeing the results, you can think, okay, this port is more useful for the complex processes, but in my case, I prefer to to test this application for the non-complex process, the electron-anti-electron, muon-anti-muon process, and I apply the same idea that the MADGRAPH GPU group. I port the matrix element calculation part, and this is the algorithm. I set the number of events, and I extract my IP, written in HLS, the momenta and the matrix element calcul for each event. So I developed this on BT's HLS. I obtained the binary file. I write the host application for my board, in this case, the Alveo 250, and the host is my desktop. And you can see the flame graph. This is the matrix element. Well, this part. This part is the communication via the GPU and FPGA part. And this is the calculation of the matrix element. So comparing the frame graph on CPU, the matrix element is the 40%. On GPU, we parallelize this part and obtain a reduce of 24%. And on FPGA, we reduced 80%. So this is the resources I use in my case, and this is the frequency of the FPGA, and this is the result. So for this process, comparing the big number of events, for this case, it's 57 times faster than the CPU, and 14 times faster than the GPU. So I think, I seen the results, I think, okay, the HLS let me write this application on C++. Okay, it's nice, but this language is so at a high level. So you need a translation time to BSDL, and the code it generates is not the best. So the HLS let me write this module around in two months, this port. So I think, okay, how many time it take me in writing this code in BSDL? And I think it's very time. So on the future implementations, I want to test this module, or writing in BSDL for me, and I want to increase the performance on this case. The next step is write the code for the complex process, the gluon, and test a version of the leading order processes, and finally study the implementation for the beyond standard model and the next two leading order processes. So that is all.
Thanks, Hector. Very impressive work. Maybe I can start with a question, actually. Can you go back to one of the plot you showed about performance of either CPU or FPGA? You had a bunch of these. Could you help me understand what I'm seeing, actually? Because I'm not sure I understand, like, what is the x-axis, what is the y-axis, what I'm supposed to be. looking for?
In this case, don't imagine the typical J-X axis. You think, okay, I set the initial and the final time.
Okay.
I want to do a picture of my platform. Okay. This is the time I spent, and the y-axis is the process. It's called the functions. The functions are called
Okay.
in this case.
So each y-axis is a different function or something. Or, okay.
This is the function called, and this is the time.
Okay. So each.
So, thanks to flame graph, you can detect the bottleneck. Well, in this case, this is the matrix element, and around the 40%. And in this case, this is the matrix element on GPU, and it's only the 24% of the GPU and CPU resources.
So how do I tell it's 24% based on this plot? Can I tell it's 24% based on this plot? Like, where is?
Because if you put the pointer on this, you can tell.
Okay, so you can already tell from this plot, but it is 24% of the resource usages. Okay, thank you. All right, more questions for Hector? Okay. All right.
Thank you. Very nice. Can I ask you what are the different stages in these plots? I guess that are the matrix element calculation, and then you have the actual element generation. No? But for instance, on the FPGA, I see that the trend. So for the matrix calculation, maybe this is immediate because you have all this parallelization to what I understand from this plot, and then you have that the actual event generation. It has like a growing trend. So maybe I'm not sure if I understood correctly the plot. This could be my issue, but
I repeat it. This part is the matrix element calculation, okay, and this the Python. I use the Python API, the ping Python API, to communicate the alveo with the host, and I think this part is huge because the number of events is lower, and the final time. You can.
David, you want to?
You see for this number of events, the executing time is around half second. Okay. In this half second, you have the matrix element calculation, the random number generation, and the plot. So I think the matrix element calculation is faster than the plot of the process.
okay. And just wondering, are you also doing the actual event generation after the matrix element calculation, or not? Are you doing the event generation and producing the event file after the generation, or not? After the
Yes, I do the event generation.
And the if you can go back to the. Just wondering, is there maybe some advantage in retrieving the computed matrix elements from the FPGA, maybe processing them with the CPU?
The advantage?
If there is any.
No, the advantage is in FPGA you can go faster, no, than the CPU. But I send you a.
Thanks.
One question is about, we spoke mainly here about the performance in terms of computing, but do you have some comparisons also in terms of the final results that you actually, like the actual matrix element that you're generating?
I obtained the same results on CPU, on GPU, and FPGA. I don't plot. I don't show.
Sure. Okay.
But
And for the CPU, is a single core, or you're doing is a
multi-core.
Okay.
I use all the cores and I noted this.
Thank you.
More questions for Hector? If not, I have one more. So I think you talked about the advantage and disadvantage in HLS. I guess, is there any disadvantage of using FPGA? Because I've never imagined we can do multi-color generation FPGA, to be honest. But just for FPGAs, what are the challenges you have to face to implement the MADGRAPH on the FPGA? Is there any disadvantage if we switch to using FPGA for multi-color generation?
No, the advantage in this case, I write the code in C++ and I translate in BSDL. This is an advantage if you don't know the hardware description language. Okay, this let you.
Sorry, I guess my question is not about HLS, but about FPGA in general. Is there any disadvantage of running MADGRAPH in FPGA that you can't do, for example, in the CPU or GPU, but you cannot do on FPGA for the event generation, like for the just overall the MADGRAPH? No?
I don't find any disadvantage in this case. So
really? Oh my God. Interesting. Okay, thank you. No more questions. I think we are done. Okay, let's thank you again, Hector.